Yeah, user instruction, I guess, any user, like one user, oh, oh god, stop scaring me, everyone walking past. Christ. About 100 today, about hell yeah.
My friend works at Coldstone. It's him.
Oh, the TA.
Yeah, my work.
Oh, I thought it wanted.
Harsh is like one.
Yeah, I guess be there every day.
Bob likes him sometimes.
Oh yeah, so when I was like asked her love it, she goes to the big one. And I was like, okay.
Pretty cool. Nice fiction fan.
Small ice cream bar, like 2 scoops of like ice cream from one of those tubs. And, like, I don't know what, this sounds so
I eat, but I think it's like and then that one, and I just how bad, dude. What could have been something?
I don't know, like I could have called.
Oh,
had to
something
sound
more.
more
I mean, something more dramatic.
Look at this beautiful graphic.
I love seeing it. Wow, I want to
I know, they have such nice grass. Definitely genuine, real grass.
I'm not thinking all my classes today.
Hey, just wondering if you're
Let's start our discussion today. So, do you have any questions regarding assignments and all that? Assignment, do you have any questions?
So we have to merge all data for all the users and then calculate, right?
So this part is, yeah. So if you say you only use 10 users, then only give accuracy result for 10. Don't have to do all.
But we still combine all the users' data.
No, individual users. Give individual users. Yes. Because this is user dependent. Right? So when you are training, you are using the users, only the users' data. And then testing on the same users' data. Now you can go two ways. You can have one machine or 10 machines. Not 10, if you have 37 users, let's say, you can just use one machine, or you can have 37 machines. Each machine for each user. Or you can have just one machine, where you train that machine with 80% data from all the users. It's up to you. See whichever works. My guess is nothing will work. So, yeah, as I said before, that you have to share the frustration with me. I should not be the only one frustrated. Okay, so one problem, a few students emailed me regarding that assignment. One problem is that in project 2, you might have had averaged over a lot of individuals. Right? You might have taken features that are averaged over individuals. If you take that, it might be a problem for you in project 3. Because now if you average over individuals, in project 3 you cannot do individual and user dependent analysis. Right? So there's an easy fix to that. What you do is from project 2, after averaging, whatever features you got, use those features. Don't discard them. So use those features, but now you extract those features on individual instances. So just re-extract the features that you already got. Right? So you don't need to go back and do the project 2 again and figure out a new set of features. You don't have to do that. So you just get the results from project 2, whatever features you think are important, given that you have done the averaging over all users, and then just use those features. But from those features you extract from each instance of a user. Right? So you can do that. Any other questions regarding assignment? Yes.
How can we calculate the everyone score a multi-class classification?
So that's what in the project 2 I didn't ask 3. In the project 3 I didn't ask you to do multi-class. I just asked you to do 2 class. So take one gesture and classify the data points at that gesture X and not X.
So one user classify one gesture?
Yes. So if you have one user, you take about gesture, all the data points marked as about and all the other data points marked as not about. Then you can have a F1 score and precision recall. Yeah, multi-class you can't really have F1 score. And there you just do accuracy. Yeah.
We don't need to do any one versus all or SVM, right? Like combining all the binary classifiers. We don't need to do multi-class classification. And
No, you don't need to do multi-class. Yeah, you don't need to do multi-class. Multi-class is an easy extension. Once you have one class, multi-class is not difficult. So you don't have to do multi-class. So the class before the last class we did reinforcement learning. We'll finish 2 methods of doing reinforcement learning. We'll talk about 2 methods, dynamic programming and Monte Carlo. But we'll just stop there and discuss the Google DeepMind. Maybe not in this class, maybe on Wednesday we can discuss that. But before that class, you learned some deep learning techniques, right? You saw some tutorial on Keras. Keras? What? So, was it useful, or can you write a neural network using Keras now? How confident are you? Don't think that I will give you another assignment. That's not the purpose. But just I'm asking so that I might spend. I want to see how he introduced deep learning to you and whether it was useful or not. Okay? So don't think that if you say that I'm very confident, then I will give you an assignment. Don't think like that. So was that useful, or do you want something more from it?
I mean, it's just good for the start, like to know how Keras works, but like applying from a data set is still very exploratory. So
that means you need an assignment. No, I'm not going to give you an assignment. So I'm thinking maybe next iteration of the class will have an assignment on that. So you're making it tough for the future students. Not this class. Okay, anyways, oh, another announcement, not announcement, just a note, is that for the final exam, I'm not going to give questions from the book because I have learned my lesson. Typically, a lot of students have just taken, I think the solution manual is probably available online, right? So you have just, in the cheat sheet, in very small fonts, you have just copied the entire solution manual. So there's no point in asking questions from the book. So I will just ask whatever comes to my mind and see what happens. The problem is twofold. The problem is that if whatever comes to my mind I ask, you don't know the answers, that is good. That's not a problem. But the problem is I don't even know the answer. So how do so that is a big problem. So let's see how we can solve that problem. So what I'm thinking is that we'll do this reinforcement learning, and then we'll talk about the Google's DeepMind paper, and that's it. That's it for the final exam syllabus. Right? Now after that, whatever we discuss won't be in finals. So you can keep a free mind and ask me questions or suggest me topics to cover. Those won't be in exam. And with respect to all the slides I have uploaded, if you go to the slide section, you will have Markov decision process, reinforcement learning, association rule mining, everything is there now. With respect to the videos, a lot of them are missing still. Okay, so the TA has currently uploaded 1 or 2, I think. The problem that we have faced is that different accounts were used because there are too many TAs. So different accounts are used, so we have to go into each and every account and figure out the videos. So I will upload it, maybe by the end of this week, all the videos should be uploaded. So I will make it a point to do that. Now the risk is that maybe some videos are not there, then we will have to see what we can do with that. But the thing is, the best way is not to wait for the video, just come to the class. That is the best way. A video I upload for your convenience, but I don't have to. I don't have to make it convenient for you. But yeah, I'll try and upload the video. So any questions to the last few things that we have discussed last class? Any confusion, question? Reinforcement learning is kind of confusing. I am also learning with you, so I also get confused a lot of times. So let's continue our discussion, or let's do a little bit of recap. Let's do a little bit of recap. We are talking about Markov decision processes, right? Let's look at that slide for a bit. Yeah, we are looking at Markov decision processes, and this is a way of expressing random processes, right? And we are not really interested in the outcome. If we were interested in the outcome, we would have just gone to Markov chains. That gives us outcomes. But we were mostly interested in the policies. We are saying that, okay, what policy should we take so as to maximize our reward? And that is not Markov chain. That is Markov decision processes. Right? So Markov decision processes, they deal with this problem of figuring out the best policy possible. Now the entire last class we spent understanding the difference between policy and execution of a policy. Right? So we took this example. We said that, okay, there is a robot in a room, right? There is no goal for the robot here. There is no goal for the robot. But the robot does something. It follows a certain command and it does something, or its command sequence and it does something. And when it does, it has certain rewards, some positive rewards, some negative rewards. So we said that each step it takes, it has a negative reward of minus 0.04, and each those boxes it goes to the reward at 4.3 is +1 and the reward at 4.2 is -1. Right? And you have a start state which is there. Start state. So now we are saying that we don't know what is the goal of the robot. We don't know what is the whether the robot wants to maximize the reward or minimize the reward, or is there a time when the robot stops. We don't know all those things. But can we say something about a policy that if you move in a certain way, you are always going to maximize your reward, or you are always going to minimize your reward, or you'll always be at reach certain goal? Can we ask that question? So when we ask that question, then it becomes a Markov decision process problem. Right? Now if you fix a policy, and if you fix a policy and say what the robot has to do in each state, then that becomes a Markov chain. So policy fixed is Markov chain, policy to be learned is Markov decision process. But then what is reinforcement learning? So what is it? So Markov decision process is a way of expressing a reinforcement learning problem. So reinforcement learning is much more general. So it assumes, or it doesn't assume, that there is a model, right? Reinforcement learning. So Markov decision process is a better life than reinforcement learning. So better life as in, if you have considered Markov decision process, you already know the states, you already know the actions that you have to take from that state. So you know the S, you know the T, you know the reward, everything you know. So that means you have a world model. World model means what are the consequences of your actions in the state you know exactly. So this is a Markov decision process. This is not reinforcement learning. This problem that we have in the slide is a Markov decision process. You know the reward, you know what action you will do and where, in each state, and you know which state you will end up in after you take that action. So there is a Markov decision process. But now if I tell you that I give you this box, do whatever you want, but somehow maximize the reward. So you don't know, okay, if I press the up button, with what probability am I going to go up? You don't know. If I press the, if I reach that 4.3, what reward I am going to get? I don't know. If I take one step, what negative reward I am going to get? I don't know. If you do that, and if you try to figure out as you go, right, you just start playing, you just start commanding the robot, and you figure out with subsequent observations. That problem, or in that environment, if I ask you that take a policy that maximizes your reward, the answer to that question lies in reinforcement learning. Okay? So it is a true knowledge retrieval process, reinforcement learning. It has to retrieve knowledge and then modify its policy accordingly so as to maximize something. So now the natural question, as a student asked, that why do we learn reinforcement learning in data mining and not in some AI and all that? So that's a very difficult question to answer, and that is what I'm trying to figure out in the next iteration of the course. Where to stop in data mining? Right? Where do I stop? And even where do I start? For example, if you look at the initial chapters that we talked about, PCA, is that a data mining concept? PCA. That's a statistics concept. Why would I teach PCA in data mining class? Although I taught, but why? Yeah. There's no point. So maybe those will be just your prior knowledge. I'll assume those as prior knowledge. Or maybe give you some reading exercises. So that, because I'm just teaching it as a second iteration. So Over iterations, this course will change. So it's a learning process for me too. And also the answer to this question, do I teach reinforcement learning here? I don't know, I'm just figuring it out. You tell me, should I teach these or not? Once we finish a good way to do it is do it in the evaluation. There will be some course evaluation near the end. So say that this was bad, you shouldn't have taught it. So if you give me those kind of feedback, then we'll see where it goes. Okay, so that is the reinforcement learning problem. You don't know anything, you are just trying to figure it out. So where will you use it? I can give you a data mining example. Simple, I think we have already discussed it. Did we discuss it? Where will you use reinforcement learning? We did not discuss? I thought we did.
Games.
No, games is AI. Right? The AI researchers use it in games. But what will a data mining researcher do with reinforcement learning? You know our recommendation systems, right? We have talked about recommendation systems when we talk about RBM. Right? We talked about recommendation systems. So in the recommendation systems, there is this problem of cold start problem. You know cold start problem? Cold start means a user, say for example Netflix. Right? There are thousands and thousands of users in Netflix. But when you first enroll, how do Netflix come up with suggestions? What do they show in the first page? How do they know that you like certain movie? So there it is like figuring out all those states and actions and probabilities. And they don't know anything about you, but they are trying to figure it out. So they will have some initial guess. So what initial guess should they have? And based on what you watch, how should they change their policies? That is a classic example of reinforcement learning. And not example, you can fit that problem to a reinforcement learning space. Figuring out as you watch different kinds of movies, figuring out what movies to recommend. So there are many different types of cold start. For example, it can be cold start user. Right? Cold start user means that you as a person went in first, created a profile, and you don't have any history whatsoever for a particular or for movies. The other thing is that cold start item, which means that there is a lot of users with a lot of history in watching movies. Now a new movie comes in. Whom do you recommend it to? Do you recommend it to all users? Some users might not be interested in romantic comedies, right? So why bother them with this suggestion? And some users might not be interested in action movies, so why bother them with action movies? So it's not a straightforward decision, right? When you have a cold start item. So all those problems, whenever there is a cold start, reinforcement learning plays a good part. Right? So this searching policy or recommendation policies, that's what they are learning. So basically reinforcement learning means you explore your environment, you know nothing about the environment, you explore the environment, and as you explore, you take some initial policies, some random guesses. Right? Take some random guess as the initial policy, then you start exploring. When you explore the states, you gain knowledge about the states, you gain knowledge about the actions, you gain knowledge about the probabilities, and then when you have explored for a long time, you can develop even a model. And that model will be a Markov decision process model. And from there, you can then, after you have had a lot of data, then you can evaluate the policies much better. So let's go forward and see how we do this, how we can do reinforcement learning. So there are many different methods. So yeah, this is what we have already talked about. So in order to do reinforcement learning, we have talked about this before also. We have to figure out certain reward functions. Right? if I want a policy, or if I want to better a policy, I need to evaluate a policy. So how do we evaluate? There are many techniques. So episodic versus continuous tasks. So which means that you can have certain policies or certain values that help you end the game faster. Right? Typically what happens is, as we have said, that policy, there is no time duration after which you should stop. So policy evaluation means you run it for infinite time and evaluate. But there are some metrics where you can just stop it. You can say the most recent end. Or if you reach end steps, game is over. Right? So just curtail the value function to just end steps. That you can do. Or you can have some additive rewards that you just sum up all the rewards. But there is a chance that it will go to infinite. For example, in the robot case, if you add up all the rewards without discounting, and the robot keeps on hovering around the same point, the reward can be negative, not negative. But it won't be, in that case it will always be 0. But that is beyond the point. We will come to that later. And then you can do discounting, that okay, the most immediate state, no discounting. Then state, that is one state in the past, gamma discounting, another state in the past, gamma squared, and so on. So if you do that, then you will see that if the rewards are constant and gamma is less than 1, then for infinite steps, the total value function is converging. Right? Converging towards 1 by 1 minus gamma times the reward. Right? So that is another way that you can calculate, evaluate policies. And these already we know. Right? We don't know one thing, that Q. Right? Q function we don't know. We know the value function. We have talked about that. And we have talked about the Bellman equation using the value function. But we didn't talk about the Q. Right? So what is the Q? So what is the value? Value is the expected return when starting in S and following a policy pi. So value function is fixed for a start state S. So you give it a start state S, and value function says that okay, if you follow this policy pi from this start state S, then you will get this value. Right? But then there is a Q function, is the expected return when starting in S, performing A and following pi. So now this is not just S, not just the start state. It also says that okay, this is the start state and you take this action A. Right? So start state and an action. And then after you take that action, you follow the policy pi. What will you get out of it? What value do you get? That is Q. Right? Q pi. So you can express the Bellman equation in many forms. One of the forms using Q is this, very simple. And what does it say? It says that okay, you first go to the policy and say what happens when you are in state S and you take an action A. So you go to a particular state. One state you go to. So you go to that state and from there you calculate the Q pi. Right? From there you calculate the Q pi. Or basically the value. And then you sum this up over all different actions that you could have taken when you are in particular state S. And that should give you the total value. So that is like in a recursive equation you can express the value function. And then that you can use later for reinforcement learning. This Bellman, optimality, all these things we have talked about. Right? These are mathematical details. You don't need to know about these because you won't be asked in exam. But if you really want to delve into this, you have to go into domain of mathematics. And I don't want to spend time doing mathematics here. It's just a language. Right? So we'll talk about the inner meanings of all these. So now solving a RL problem, there are many different ways. 3 ways we'll talk about. Actually we'll talk about temporal difference learning also. Maybe not in this class, next class. So we have 2 things, dynamic programming, Monte Carlo, I have planned for this class. The third one we'll discuss next class. So what is the dynamic programming approach? Dynamic programming approach is basically saying that okay, you start from state S. There are so many options, right? From state S, if you start, you can take so many actions, following the same policy. No, policy is a mapping between state S and A, right? So you can have so many options of policies. So how do I explore all possible policies in the most structured way? Now keep in mind that if you want to explore all possible policies, it's infinite number of policies. Right? Because there is no time duration gap. There is no gap, time duration cap. Right? There is no cap. So if there is no limited time, then the number of policies is infinite. So they will never stop. Now you have to put some constraints. You have to say if two policies have the same value function, just choose one. Don't explore all others. Right? So there can be different assumptions such as greedy assumptions. We will come to that a little bit later. But dynamic programming is saying that okay, basically it has two main components. First, to assume a random policy. Right? Initially you don't know anything, so just assume something, some policy. Right? Then you estimate the value function v pi of that random policy. And then you change the random policy v pi, random policy pi, such that v pi either increases or reduces, or basically you optimize v pi. Right? So it is basically not really trial and error, it's iterative improvement. So you never make v pi worse, you always make v pi better. So that's not really trial and error, but it's iterative improvement mechanism. So it has two parts, policy evaluation and policy improvement. So you start with an arbitrary policy and you repeat evaluation improvement cycle until you see that value function converges, it never changes. Right? Now the assumption here is that there is a value function that never changes. It might be an infinite value function. For example, if you just add up rewards, it's infinite. Right? So for this to work, you should have a value function that converges. If you don't have it, it won't work. So there are these examples of value functions. We have already seen this, the iterative value function, step k plus 1 with respect to k. These are all FDP concepts, right? So these are very well and good if you have a model. If you don't have a model, these don't work really. So that's what they're saying, that you first evaluate policy using the v pi equation and then you improve policy. So how do you improve policy? There are many different ways to improve policy. You can just go and change the action in a particular state. Right? That is one way of changing policy. Now so this assumes that you have a NDP. So if you have an NDP, then you know if I change the action, what state I go to, you know, right? So you can do that, you can change the action of one state, or you can change the action of all the states. So what do you do? So many different options there as well. And you have to figure out a change in policy that is strictly better than the previous policy. And you never go and use a policy that is worse. Right? So what you can do is you can check the states one by one, right? And then 2 by 2 and 3 by 3 and change them and figure out. So again the space is exponential in number. Right? Not exponential, combinatorial, which boils down to exponential number. So then what you do is, okay, so you start with policy, pi 0 is an arbitrary policy, then you go through an evaluation cycle. So you figure out a v pi 0, right? And then you go through an iteration where you want to improve the policy. So you get pi 1, a different policy, then you execute that policy and evaluate it, and then again you improve, evaluate, and finally you will go towards the optimal policy. If you run for a long time, you might end up with an optimal policy. So that is what the dynamic programming does. So these questions, can we use DPE to solve robot in a room diagram? Let's talk about them later, because we haven't really applied these solutions in practice, not yet. Then the second type of solution is Monte Carlo methods. Right? So anybody knows about Monte Carlo in general? Like, what is a Monte Carlo simulation? Anybody has idea? Randomized simulation. It's a very old concept. Right? So anybody knows about particle filter? Particle filter is an example of Monte Carlo simulations. Kalman filtering, EK, extended Kalman filter, Kalman filtering. That is not Monte Carlo. But those are some examples of iterative improvements, iterative design improvements. And those do not really follow an algorithm, it's a randomized simulation solution. Right? So what is this? So one example is particle filter. So what is particle filter? So let's say you have an objective function, right? And you want to reduce or maximize, minimize, whatever you want to do. And this objective function depends upon initial state vector x. Right? So state vector x and function of that x is the objective function, and you want to reduce that. But you don't know what x is. Now you also couldn't find any structure to that problem, so that you can use linear program or non-linear program, whatever. You cannot use that. If you cannot use that, then what do? You just do whatever. So Monte Carlo is the organized way of doing whatever. So what do? You take x, initial guess, right? And then you assume a probability distribution. So what is this probability distribution? You are saying that okay, if I take x, the optimal solution will have x's that lie in the general neighborhood of x, of the initial value that I chose. Right? That is your assumption at every step. So in the first step, you are assuming that okay, I chose x0, I chose it randomly, but my assumption is that the optimal x, so the x for which the objective function is minimum or maximum, that is somewhere in the neighborhood of x. So what you do now is that following a probability distribution, you choose 1000 x's around this initial point. 1000, 2000, 10,000 is your choice. So what can be probability distribution? Maybe Gaussian. So you choose 2000 data points in such a way that it has a Gaussian distribution and the mean is x, the initial value that you chose. Right? So now you took this 1000x. Right? Now you evaluate the objective function for all these 1000. Figure out which one has the best value. You rank this 10,000 or 2,000, 3,000, whatever you chose. You rank those 3,000, 4,000 points with respect to the value of the objective function. Then you take top 500 and by just random guessing you take maybe 10 or 20 from the bottom 500 and you mix them. You make a 520 data point population. Right? Then from that population, for each sample point, you repeat that process. You take this sample point, make a distribution, take a lot of points around it, figure out the compute the objective function for each point, and take the first 500 and 10 or 20 from the last. In each step, you should maintain that the number of data points is not increasing; it's remaining the same. Don't increase the number of data points because it will keep on increasing. Then you do it for maybe 40, 50 iterations, and then you get a population, and you take the best in that population. Now that is your Monte Carlo simulation. Now there are many different manifestations of Monte Carlo simulation. One is this particle filter I talked about. The other is genetic algorithms. type of, they are a bit different from Monte Carlo simulations. They are more advanced genetic algorithms. They are different stages of how they select points. They may not follow a distribution. They have concepts of mutation and all that. However, let's not go there. Right? So genetic algorithms is on evolutionary algorithms, swarm optimization and colony optimization. All those techniques are there. Those are all heuristics, basically. They don't follow any program structure. They don't follow any problem structure. When you are at your wit's end, you don't know what to use, you use this. That's why I don't really prefer. So, and reinforcement learning is a very good example where you should use this, because you are really at your wit's end, because you don't know anything about the system. Right? So just let some samples explore. So let's talk about Monte Carlo. So Monte Carlo doesn't need the full knowledge of the environment. That is a very important distinction from dynamic programming, because we said that dynamic programming at least needs the MDB. It needs the MDB, because otherwise it cannot calculate the value. Right? So, but Monte Carlo methods do not need full knowledge of the environment. It just needs some experience or even simulated experience. So this means that Monte Carlo method needs you to explore a little bit. It cannot start immediately. It needs you to go do whatever you want and see what is the reward. If I do this, what happens? If I do that, what happens? And you have that knowledge, you gain that knowledge. Right? Or even it can be just a simulated experience, which means that simulated can be assumptions, or it can be in a different domain, some experience in a different domain. Right? So simulated experience can be assumptions also. But again, similar to DP, it has policy evaluation, it has policy improvements. Right? So the thing is, since it has policy evaluation and it has policy improvements, if it doesn't have the model, how then does it evaluate policies? How does it find out values of the policies? So what it does is that if you want to estimate V pi s, V pi is the value of a policy pi starting from the state s, then what you do is you have to, you can use this, that expected return starting from s and following pi minus estimate as average of observed returns in state s. So what does that mean? That means a very simple thing. You just execute for a while. Execute for a while, following a policy, say random policy pi, you just selected one. Execute it for a while, see what value you get. Right? And that forms a measure of the value estimate of a policy. So it's just what you get. Execute that policy and see what you get. So that is what, there are many different ways of doing that. So one way is first visit Monte Carlo. So what is first visit Monte Carlo? It says that, okay, you start from an S0 and you want to estimate V pi s, right? You want to estimate V pi s. So you start from S0, follow this policy pi. You start from S0, the first time you reach S, you start calculating from that point onwards. So first time you reach S, you calculate what is the average reward that you get from there on. So if you see that, okay, the first time I reached S is there, and I keep on calculating, I figure out the rewards, -1, +1, -2, +1, -3, +5, so that becomes the reward is +2. So if I use policy number 1, my reward or the value is +2. Right? Then I might choose to do something else, so I have a lot of iterations. So this is the exploration phase where I don't have the model. I do a lot of iterations and I only calculate these rewards. And I only calculate these rewards. And then what I do? I have a lot of observations like this, I average them. And that becomes the value of that policy. starting from state S. Right? So without even having the model, I just let some agents explore the environment, and I got a evaluation of the policy. Right? So that is how this Monte Carlo method works. So it doesn't need a model. It doesn't need an MDP. Now the problem is, yes, V pi, the one that you get from that type of evaluation, is not the exact value. Right? If you had a model, V pi would have been exact. But you don't have the model, so you can't really do much with V pi the way you got it. But if you take a step back and if you say that, okay, what about Q pi s? Can I get some estimate of Q pi s? So Q was what? Q was if you are in a particular state and you take an action, A, right? You take an action and then figure out what is the subsequent value. Right? So now if you take an action, the moment you fix an action, you get the reward. Right away, right then and there you get the reward. The problem with value is you didn't know what action to take. Right? When you calculate V by S, you don't know what action to take. There are multiple actions available. So which action leads to what reward, what state you don't know. But Q pi doesn't have that assumption. Q pi tells you what action to take. Right? And then you sum over all actions. So that might be another way. So instead of improving V pi, why don't you improve Q pi? Right? So what is improving Q pi? It says that, okay, you take an arbitrary policy initially, then you evaluate Q pi 0. So take this policy and you evaluate, okay, if I start from S and I immediately take this action A, what is the reward? I know what is the reward. Right? So that is Q. I get Q. And then I try to improve Q. How do I improve Q? By just changing that immediate action. Yeah? Because if I change that immediate action, only that is going to change Q, right? So I just change that immediate action and I change Q. So the problem becomes easier. But there is a huge assumption. Do you understand why the problem becomes easier? If I change from V to Q, why does it become easier to solve? Yes?
Because you only take one step.
Yes, so V means that you don't even know the first step. V says that what is the value of this state. If you follow the policy pi from this state, what is the value? So you don't even know what actions I have to take. Right? But when you talk about Q, Q already tells you the action. Q is S, comma A. Right? Those are the two inputs that Q takes. And Q only depends upon the immediate action that you are taking. So if I follow this policy, instead of pi 0, evaluate V pi 0, then improve pi 1, then evaluate V pi 1. Instead, if I just do Q, then my immediate actions will affect Q. My immediate actions might not affect V, but it will affect Q. Right? So if I choose the best Q at a given time, then that might lead me to a particular solution. But there is a big assumption here. The one that I stated. The assumption is that if I optimize Q every step, then I will get to the solution. That is a big assumption. What is that assumption called?
Greedy approach.
Greedy approach. Yes, that's the greedy approach. It might not work. Right? It might not work. In some applications it might work, but in some others it might lead you to a local minimum. But that is a problem. If you convert convert from V to the Q domain. So yes, greedy policy won't explore all actions. So that's the problem. So what you do, what you can do is you can select between greedy and dynamic programming in a not dynamic programming. You can select between greedy and exploring all possible approaches, right? With certain probability. You can say, okay, this is epsilon greedy, which means with probability 1 minus epsilon from the greedy action and with probability epsilon perform some random action. Right? So you can have a portion of actions that are just random, just you thought about it and this part of the neuron. Right? So that you can do epsilon greedy policy. So and another example is so the previous one says that you need to have some experience. Right? This requires some experience. So you can either just start doing the exercise and get experience, or you can have some simulated experience. So card games, and this slide has this example of card games, and says that in case of card games you can have simulated experience also. And from simulated experience you can gain knowledge about the environment. But in case of a robot control, or let's say in Mars you want to control a robot, there you cannot have simulated experience. Right? So in certain cases you can have simulated experience, but in some others you may not. Controlling robots in Mars, you surely not have simulated experience. So the Monte Carlo in summary is that it may not find optimal solution, but it is much faster. It is much faster than dynamic programming, because dynamic programming tries to explore all possible solutions and comes up with the best. But Monte Carlo does not explore all actions. So it is kind of hit and miss. Then we come to temporal difference, which I didn't plan on talking about. Well, let's talk about this a little bit, since we have time. So temporal. So there are advantages to the Monte Carlo. There are disadvantages to it. There are advantages to dynamic programming, disadvantages. So temporal difference learning tries to combine Monte Carlo and dynamic programming in some way. So in Monte Carlo, if you take the greedy approach, it only takes the immediate step. Right? It never goes back. Dynamic programming can go back because it says that you can change with the policy improvement process. Policy improvement process can change policies in the stage that you have left. Right? It can also do that. But Monte Carlo doesn't do that. Monte Carlo says that, okay, whatever queue I have learned, I have optimized now, don't look back, go forward. But the temporal difference learning can look back. So you can control how much to look back, right? And how much policy change will affect previous steps. All those things you have control. So then there are some ratios, as you know, that alpha, gamma, those are the ratios of how much, right? What is the control between the greedy approach versus the dynamic programming approach, how much do you control. So that is basically temporal difference learning. Oh, it's gone. This one also doesn't want me to discuss. So let's actually stop here, because there are all these things by book and all that, so you don't have to, and there are some backup slides. You don't have to talk about it. So we'll stop here with reinforcement learning. The next topic that we'll talk about is we'll read that paper. I haven't uploaded the paper yet. I'll upload the paper today, and you read that paper, and we will discuss that paper next time. And in the meantime, if you want me to discuss certain other topics, you tell me, and we can discuss those. But they have to be related to data mining. So let's see what you find out. What is related to data mining? Okay, so you can go early today. See, what we have decided is that everybody is having a different answer, and I cannot, some of the answers I cannot do. So I'm giving marks to everybody. Yeah, come. No, Wednesday. Monday or Wednesday. Yes. Comprehensive, but mostly after the.
I even mailed regarding this, saying that
so wait today. If you see that the problem still exists, then
No.
You extract the same features from the other actions.
Okay, so we have to pass the data of other actions with the same
Feature extraction.
Then that will be the alien machine. Okay, and then when we like for different users, we loop it to get an accuracy or
Yeah, you can do that. Yeah, you can do that. You can do just whatever decision you do, just write it.
okay. We loop it and get different accuracies
Do you agree with all these?
So right now what we are doing is since there is a date only like 6 or 7 and what we do feature 1, 2, 3, 4, 5 values. So feature 1 value from 1 to 6 we have taken this and then again feature 2 value from 6 to 7. So we have taken an assumption that made like that is like action performed and we are feeding this to the
Yeah, that's
so we can do that.
yes.
Seven users I'm taking. So each user has to perform this many actions.
Like about
Yeah, so this will be a matrix of 10 plus 7.
What can the
10 actions.
So what is this?
That user one has performed 20 about action 20.
Because we have some filter out some data that has more than 50 entries or 55 entries.
Oh, that's fine, but why
But
do
we
you
have to do that for each user. We need to divide 60% of the data.
Yeah.
So for that I need a count. But how many times he is?
Oh, yeah.
Just like
That is just
yeah, that is
pre-processing.
so my files on which I will perform the classification things. It will be for user one about and not about, right?
Yes.
So when I'm doing that, user one, or let's say he has performed about 20 times. So for training, my action should be 12,
Taking 60%.
taking 60%, and not about would be entire this things 60%, right?
Yes.
Okay. And so I was confused that we are not doing this about and not about for all the users combined.
No, for each.
For particular user only.
Yeah.
And so after doing this, we found that this isn't very bad. This is
Very good.
the true positives will be very less because testing will be done on only 8 things. So
That's good. What else have you done?
all the
Which one is giving you best?
so neural networks every time it has a different
Answer.
yeah,
Because it's
and yeah, for decision tree and SVM the results are always same.
is bad for SVM.
SVM no, they are giving good results.
SVM is
Good as in precision is ranging from around 0.4, 0.6, 0.7 and recalls are 1. Like
So what
true
is the
negatives as in false negatives are less, are 0. That false negatives are 0.
Oh, that's great.
That's great.
Yeah.
Yeah.
Okay, that's good. That's good. Okay. Yeah.
So we were
So SVMs are better in the class invariance problem.
yes. So we were like really confused because if we are not getting any true positive, precision and recall both are 0 and hence effort score will be NaN. So denominator becomes n. Yeah.
No, but in that case, you just don't report the account.
Okay. And the report will be good if I am presenting.
Oh, I need to upload a good bad report.
Oh.
So I'll upload that.
Okay. log for each of them.
全场一共10几万个数据，只有
Thank you so much.
所以你要把其他的格子的选一部分后面的，不要全选，
You
选
can,
部分。
yeah.